Ugh, that's not good. Good morning, all. Monday is upon us. Monday. Monday. Let's see. Let me show you a couple of things. So there's one class of equations that I've been alluding to now and again, and today is the day to understand those. So let's take a look at this example. So again, this is I'm just doing this by way of we're barely awake, and let's get our mind going this morning. But this is all data that's in our Math 96 course, kind of an applied algebra course. So you can probably appreciate this is a set of data that somebody would find interesting. This is kind of what happens when you have a baby. You go to the pediatrician and you check in every so often, and you know, the pediatrician pays attention to how old your child is and how much they weigh or how long they are, just to make sure they're kind of eating enough food and all that, make sure they're getting going in the right direction. And so here's what that data looks like for one kid, age 1. And again, just notice the beauty of algebra, speak the language of algebra, age 1, month, 153 ounces, and so forth. You get bigger and bigger. And that by itself doesn't tell you much until you stick it on a graph over here. And you see that it's kind of increasing quickly and then beginning to level off. And that sort of makes sense, because isn't that what you do? I mean, didn't you increase weight until you kind of reached a plateau, and then you kind of hang out about where you are for the most part? And so there's kind of a trajectory that humans, and frankly animals too, follow. So awesome. You know, again, this is what algebra is hey, I found a relationship here, and now I can, if you've taken a stat course, you can even tell a parent, you know, is this danger, is your child dangerously below the trend or dangerously above the trend? Is it unusual? Maybe you know what a standard deviation is. And that's kind of all based on this logic. And so let's see what kind of an equation might model this. So if I go in here to do regression in Excel, I say add a trend line. Well, the trend line's already been added, but let's take a look at a graph. Notice a linear graph is terrible. That doesn't work very good. It's not straight. Exponential wants to curve up, whereas our graph wants to curve down. Well, excuse me, it turns out the one that was on there is logarithmic. Logarithmic graphs want to take that shape, if you will. And then again, I want to say you should know that from algebra, from Math 111, but I doubt that necessarily sticks in your head. And so, you know, I could try some others, but let's just stick with that one, since it's pretty good.
Don't logarithmic functions generally kind of correlate with nature anyways, or am I wrong?
Yeah, things that kind of work their way up to something and then level out there, like a population, for instance, might increase. Like if some plant gets in a new area or an animal gets in a new area, it might increase, but then it kind of levels off at the carrying capacity of that. So yeah, there's a lot of things in nature that kind of behave this way. You're exactly right. And again, the point of algebra is that, oh, look, here's the equation that models your child. And, you know, unfortunately, you might say, wow, that's a complicated kid. Logarithms. Hopefully you speak the language of algebra well enough to say, hey, cool, we have this algebra equation where the x-axis is their age in months. And so notice you can predict the future now. Like you could say, okay, 12 months, 1 year. Like we could use this equation, throw in x is 12. You don't have to know much, except for there is an ln button on your calculator to throw in x is 12, type 47.443, natural log of 12 plus 147.61, and that would spit out y, which is weight in ounces. Notice this is a good graph in the sense that it tells you what x and y are, tells you what the units are. And so I could actually predict the baby's weight based on this. Now notice, though, the curve doesn't work perfectly. Like this is the real world. Notice there's a lot of data that's pretty much right on that curve, but this one is really low. Was that a tough month? Is this not a good model? Notice it seems to be, is this one up here, this last one that's kind of high, is that indicating that this function isn't going to predict very well, like very far? We certainly can't take this out to 36 months or something, since we only have up to 9. So, there's those considerations, which is kind of a statistics, even a regression related thought. And of course, you should be able to work the other way around, which is kind of cool in nature. If you go measure the weight of, say, some animal that you found in nature that was sick or whatever, you're a vet and you measure the weight, you can't know an animal's age, but does it make sense if you threw in a weight of, say, 250 ounces into this for Y? You should be able to solve for X and sort of predict what its age would be. That's kind of cool in the animal kingdom. So that's algebra. Now, what are we doing with calculus? We're saying, hey, let's figure out rate of change. Let's figure out, well, in this case, change of Y over change of X. That'd be change of ounces over change of months. So that'd be ounces per month. Oh, okay. How fast are they growing in ounces per month? How many ounces per month should they be growing when they're 2 months old or 3 months old or 4 months old? How many ounces are they supposed to grow this month? Taking the derivative of this would have let you in on, their growth rate. As I've been trying to get you to understand in the big picture, algebra is really cool, but calculus adds just one more thing to this, which is the rate of change at any given point in time. So if I'm a mom or dad and have a little kid, like I might be interested to see, in that month, did they grow as much as calculus would have said they would have grown? Well, you should look at this and say, uh-oh, I don't know how to take the derivative of natural log. I've been alluding to the fact that we've been ignoring that. And now we have the skill, because of implicit differentiation, we have the skill to build the answer to this question. So that's kind of cool. So I think I will, let's see, do I have any way to get this into my computer besides taking a picture of it? I don't think I do. That seems archaic, but I think that's all I got. I think I'll take a quick picture of this and maybe we'll bring it in. Maybe I'll bring it into the notes for later. So let's go figure out how to take the derivative of that statement, and then we'll do it. The picture has been taken. Sharing my other screen. Coffee.
Yeah, I have to have like 6 shots of espresso to get functioning in the morning.
Yeah, I hear you.
This neat little stovetop espresso maker. It's great.
That's what you need, something that won't let you down.
We won't talk about me recovering this morning. I think I killed a 12-pack last night.
Dude, that was a mistake.
It was a bad night.
All right, so let's figure this out. Fortunately, this is actually pretty easy now that you know implicit differentiation. So we're sitting here with, and again, I just want you to understand that this is not the first time we've done this. There was a time when we said, okay, we know how to take the derivative of x squared, and we found the power rule. But there was a time when we said, I wonder what the derivative of that animal is. Like that, the power rule is not going to work for that. And then we also had y equals e to the x. And we're like, what's the derivative of that? And And we found those, and sort of now we have y equals the natural log of x, or the log of x. I'm just picking natural log to start with. And so let's take the derivative of that. Well, again, natural log is an action on a number. So if x is 2, I could take the sine of 2, or I could take e to the 2, or I could take the natural log of 2. Those are all operations, just like square root or plus or any other math operation. And so, I wonder what the slope of a natural logarithm graph would be. Well, fortunately, you perhaps remember that you can transform this into e. Like, you don't have to leave it that way, if you will. So let's see if we can use that fact. Remember that natural log has kind of like square root has a 2 there that you just kind of don't bother to write. Natural log has an e down there for its base. The base of a natural log is an e, which means if I switch this from its logarithmic form, it's too early to spell that hard of words. Logarithmic, if we switch it to exponential, that would be e to the y equals x. This is its exponential form. I already spelled wrong. Exponential. Don't have time to go back into that, but that's something you should know from Math 111. You can switch forms from logarithmic to exponential. So, well, let me say this really quick. If you're sitting there with something like, 5 to the x power equals 17, and you're trying to solve that, and the answer must be less than 2 because 5 squared is 17, you might remember that that's the exponential form. And if you switch it to logarithmic, that's x equals log of 17 base 5. Like, and if you can punch calculator buttons with log of 17 base 5, that tells you the answer. So logarithms were invented to get exponents alone, if you will. And that's all we're doing over here. We're just going the other direction. So you're sort of maybe used to going this direction. And if you look up here, isn't that the same thing we just did? Except for I used it to go backwards, if you will. Anyway, we can talk more about that after class if you would like a refresher on that. But this, I can take the derivative of this. You already can. You can do that right now. So I'm going to give you a second. If I told you the equation was e to the y equals x, and you took the derivative of both sides, that was the beauty of what we learned in 3.8, was that you treat derivatives like an algebra operation. You just take the derivative of both sides. So could you take the derivative of both sides of that and solve it for y prime, since the original equation was y equals natural log of x? You have the skills to build this for yourself. You don't need me to do it. Well, we said the derivative of e to the junk was e to the junk, so that's e to the junk. But since that y is, well, junk, chain rule says times the derivative of the junk. There's the derivative of the left side. Again, what we're doing is taking the derivative with respect to x. That's why the derivative of y is y prime. And on the other side, super easy. What's the derivative of x with respect to x? Well, that's just 1. So you took the derivative of both sides. So doesn't that mean y prime is equal to 1 over e to the y? And since it is true back here that e to the y is equal to x, I could replace that with x, make it 1 over x. So what are we saying? We're saying if y equals, that's not an equals. If your original function is the natural log of x and you want to take its derivative, apparently y prime is 1 over x. That's on your note sheet. So just to give you time to soak that in a little bit, we started with y equals natural log of x, and I threw the e in there just to remind you there is a silent e sitting down there. So there's a silent e sitting down there that we don't usually bother to write, and we said, I don't know what to do with that thing, but we were able to transform it. Since logarithmic form and exponential form are two ways of saying the same thing. And again, this isn't as weird. I'm going to erase this, but it's kind of like if I said x plus 2 equals 9, and you said, hey, can you make a subtraction problem out of that? Yeah, I could subtract 2 from both sides, or I could add 4 to both sides. Or maybe I'll make up a simpler example. If I even said something like 2 plus 7 is equal to 9, you could remake that problem as 9 minus 2 equals 7. Like you transformed it from an addition problem into a subtraction problem. And so the logarithm world is just more complicated. But the fact that we can take a problem that's logarithmic and make it exponential, and it's like, oh, exponential, I know how to do those. I know how to find the derivative exponents. And so let's do it in that form. Let's solve it in a form we already understand. So the only thing surprising was that once you get it to sort of look like this purple example, taking the derivative of both sides of that, you should be able to do that now. And then you get y prime is 1 over e to the y when you solve for y prime. And then since we said e to the y and x are the same thing, that's just another way to write it. So really what we're saying then is, in the language of chain rule, natural log of junk is 1 over the junk. I mean, that's the way to look at this. And if that junk is just a little more complicated than that, then we just need chain rule. So let's just do one quick example. If I said f of x equals the natural log of, I don't know, let's make it the sine of x. Again, this is mathematicians being crazy. Why would you have a function like that? Why would that model something? Well, it typically wouldn't. We just saw a model for a baby's growth a minute ago, and it wasn't this complicated, but it had logarithm in it. So we'll go back and do that in just a second. So what is f prime of x equal to? This theorem, this truth, this formula that we just built says the natural log of x is 1 over x. And so when you're sitting down here and you say, hey, this is natural log of junk, then its derivative is 1 over the junk. Just because that's not an x doesn't change anything. Natural log of junk, derivative natural log of junk is 1 over the junk. But chain rule says you're not done. What do you still have to do?
Multiply it by the derivative.
Multiply it by the derivative of the junk, because that's, again, that's why I keep using the word junk, because it's complicated. It's confusing. It's not just x. Times the derivative of sine of x, which is cosine of x. That's kind of interesting. Who remembers another way to write cosine over sine? Cotangent. Again, that's just algebra or simplification. And I don't think it's simpler. Like I'd rather leave it as cosine over sine because I feel like I understand those, or I can look on the unit circle and tell what the answers to those questions are. For instance, if somebody said, hey, that's not what I want to know. I want to know what f prime of pi over 3 is. Again, kind of a book assignment sort of a question. In other words, I actually want to know the slope of this curve at pi over 3. I would find myself wanting to, well, I don't, the unit circle doesn't tell me what the cotangent of pi over 3 is, but I can look up the cosine of pi over 3, and I can look up the sine of pi over 3. Now, just to give you a chance to soak this in, let's see if we can, let's go ahead and do this. And I hope you have some sense of, I don't know, wonder to you that
I have
you
a
just think,
question.
I don't get
So,
that. Let's see if it works. Yeah, go ahead.
If you would you multiply sine by the derivative of x? I mean, I know that would be 1, but if x were something else.
You're saying it even x wasn't x, like this was even worse, like this x was like e to the x or something like that.
Yeah.
That's exactly right. So you'd say, okay, the derivative of sine of junk is cosine of junk. So then this would be the cosine of e to the x, and then you'd say times the derivative of e to the x, which is e to the x. That's exactly right. It'd be like multiple steps, which is, again, terrifying.
Okay, thank you.
That's a good question.
Yeah,
So,
I was going to say that, I mean, you said the unit circle doesn't show you cotangent. We were suggested to us last term with Annie to go and write like the values of tangent around at least half of your unit circle, because I mean, you'll know that what, on the other side, it's just negative of whatever you have.
that's
And
exactly right.
if you had the reciprocal of that, then you would have cotangent.
Yeah. Or even just to make this huge chart that lists them all.
Had to, but that's,
Yeah. So I'm looking at my unit circle chart. I'm looking at pi over 3, and I'm seeing the cosine of pi over 3 is a half. And I'm seeing the sine of pi over 3 is square root of 3 over 2. So let's see, to divide fractions, you multiply by the reciprocal. Oh, isn't that fun? The 2's cancel. So you get 1 over the square root of 3. And just to scope that as a decimal, my calculator says 1 divided by the square root of 3 is approximately 0.577. So again, I find myself, thinking what you should be thinking out loud is kind of like, here's this weird graph, and let's go graph that in a second. And, we're putting two things together, that sort of don't talk to each other much. It's really weird. And we're saying, if you go on this graph and you go to x is pi over 3, that the slope right there will be 0.577. Like, don't forget, that's all we're doing in calculus is just taking the weirdest curves ever and trying to figure out what the slope is. Let's just see if this works, I guess, just to give you time to think about it a little bit. So we said f of x equals the natural log. I wonder if I can type just ln, or if I have to go over here and actually find the function. I don't know. I'll find that out in a minute. Of the sine of x. Dun, dun. So I get this graph, and so that's interesting. So it's like a bunch of parabola looking things that all stay below the x-axis. And so we can think about that a little bit. But first of all, let's go to the point we were just describing. So we're saying, hey, let's go find the slope someplace on this curve. And so what point did we go to? Well, we just said, and I only picked pi over 3 just because I wanted it to come out accurate. So if I say, well, let's graph the point. If I go pi divided by 3, that's my x coordinate. And then because of the language of algebra, instead of figuring out the y coordinate, I can just say, well, f of pi over 3, and then I don't have to figure it out for myself because I'm lazy. No, I'm not lazy. I'm just smart. Don't want to waste my time. So there's our graph right there. So there's our point. Notice there are points I could have chosen that don't even work. Like if I said, what's the slope of this curve when x is 5? Notice there doesn't even appear to be a curve when x is 5. So that's kind of interesting, but we aren't going to go down that road. What do you think? Does the slope of that look like 0.577? Can't be that accurate, but at least it looks like a low positive number, doesn't it? And of course, we can just go into Desmos and really cheat and say, what is the slope f prime? That's not prime. F prime of pi over 3. We can ask it. Check our work. And sure enough, it agrees with the math we just did. Apparently we took the derivative correctly. Apparently the derivative of natural log of junk really is 1 over junk. It's working. Again, I showed you that not because you think I was probably lying to you and I need to be checked, but just to give you time to kind of soak on this and think about it a little bit. No, that's not. I've noticed old people are bad at screen capturing. I'm old people, bad at screen capturing. So that's kind of cool. What's bugging you? What are you thinking? What's on your mind? Is this working for you? You need practice, but so check. Seems to be working. Let's see. Let's go back to the probably lousy picture I took of Excel a minute ago. Crop that down a little bit, make it as big as I can. Get rid of some of that extraneous junk. So what's the derivative of that? Notice it's not so bad because it just says natural log of, well, x. Like you don't have to, it's not chain rule. It's just natural log of x. It's not actual log of natural log of junk. What do you do with the 47 in front of that?
Would you put it 1 over that?
Not over the 47.
Would it just be product rule?
Yeah, there's 2 ways to look at it. One of them is product rule, isn't it? 47 times natural log of x. So I'm going to write this up here and erase it. If you have 47 times natural log of x, isn't the product rule say, well, the derivative of 47, which is 0, times natural log left alone, plus the 47 left alone, times the derivative of natural log of x, which is 1 over x. So as we've been saying by way of a shortcut, notice in the end, it is product rule, but in the end, because 47 is a constant, this first term ends up dropping out. And so the constants in front just come along for the ride. It's almost like they're not there. Just take the derivative of natural log of x and then multiply it by 47. But again, that's just a shortcut, product rule. What about the 147? What about this number? What's the derivative of that? Notice we love plus signs. We're extremely happy to see that plus sign because that means we can just ignore that until later.
It's 0.
0. So I don't know if I need to round this accurately, but let's just leave it what it says. So the derivative of natural log of x is 1 over x. And so there's our derivative. Now you could rewrite that as 47 over x if you want to, or 47 times x to the negative 1 power if you want to. But take a look at the graph. What's y prime then of 4? And this is something I would ask on a final exam. Like, can you tell me what y prime of 4 is now? And then more importantly, can you describe what that means to the mom? Mom's in having her baby weighed at age 4 months. And you tell her, awesome, your baby weighs 214 ounces, according to the chart. And now you tell her what y prime of 4 is. Of course, you leave out derivatives and all that stuff. She doesn't want to know calculus. She just wants to know if the kid's okay, right?
That would mean that they were growing at 11 ounces a month at that point, or not sure about the rate.
get the units back in it. Like look at the units of y, units of x. Don't forget that we're talking about change of y over change of x. So when you take 47.443 divide by 4, you do indeed get about, let's call it 11.9. But remember, that's 11.9 over 1. What are your y units? What are your x units? Put them back in. Like you don't have to memorize anything. Just understand what slope is. It's a rate of change of y over change of x. The y was ounces. The x was months. And notice those are both positive. So you would say to that mom that I would expect your child to be 12 ounces heavier next month. That's all you would say. If they came in at month 4 and you had charted these first 4 data points and found this equation, again, this to me seems like the kind of stuff that would get you a job. Other people just come in and say, yeah, I like babies. And you say, no, I know how to speak the language of math. I can find an equation that models the growth of this animal if I'm a veterinarian. I can find this equation. I know how to use this equation to predict things. I could use this equation to predict their weight next month. But I can also, when it's useful, take a derivative. And this tells me that at that point, their weight is increasing at 12 ounces a month. Now it's not the same next month. Next month, it'll have a different rate of change because it's leveling off over time. Is anybody bothered by the fact that the slope is 12? Does that graph look like the slope is 12? Why does that look so weird? Something wrong?
Yeah, well, you got to look at the bottom is in a scale of 1, 2, 3, 4. It's a scale of single units, and then the other one is in a scale of 50.
Yeah, like this is length 1 down here, and this is length 50 up there. So this graph is kind of tweaked just to get it to fit on a normal, and this is what graphs look like. It's kind of deceptive. So you can't rely on the picture this time like you can with, well, the boring example that I just made up a second ago. So this is what calculus does. This is how you handle natural logarithms. Lovely. Let's just do a couple of random examples then. Like I'll just give you a second to see if you can do this yourself. If I say f of x equals, let's see, what do we want to do? There's a mess. Involves everything you've learned in this class so far. Natural log is in it, which you're no longer confused by, but it still kind of looks like 3.7, where you just have a big mess of stuff now. I'm just going to give you a minute. Maybe you won't get completely done. This multiplication sign should be screaming product rule at you. If you did not see that, you will get this question wrong. You have junk times junk. And you even have the natural log of junk. So there's all kinds of stuff that should be in your mind. Like that's not just natural log of x. So you should be thinking, oh, chain rule, because it's natural log of junk. Notice it's just cosine of x though. Notice it's not cosine of junk. I could have made it cosine of natural log of x or some ridiculous thing. But you should be saying product rule. If you find yourself overwhelmed, as I've been saying, don't take any derivatives to start this problem. Say, well, the product rule says the derivative of cosine of x, and I don't want to write that down right now because my brain is overheating. As soon as you get this, you shouldn't write this step down anymore. You should just do it. You know the derivative of cosine, just write it down. But the product rule says cosine of x times the natural log of, well, let's do that. The natural log of x squared left alone plus the cosine of x left alone times the derivative of the natural log. So just so that I don't forget the product rule. Okay, good. I got the whole product rule written out. I haven't done anything, but now I'm going to go back and figure out what those derivatives are. Okay, that's the derivative of cosine of x. I look it up on my chart because it's been a long time and I'm starting to get it all confused in my mind. That's negative sine of x. And that's multiplied together. Don't have to do anything with that. You can't collect sine and natural log together. They're just apart. Fine, who cares? And then cosine of x comes along for the ride. And then what about natural log of junk? What's the derivative of natural log of junk? 1 over the junk. Doesn't matter what's in there. Natural log of rabbit, 1 over rabbit. But that's this chain rule because that is junk. Derivative of natural log of junk is 1 over the junk times the derivative of the junk. Since the derivative of x squared, thankfully, is just power rule. Again, we're done now. That's the answer. Can I clean it up a little bit or write it some different way and whatever? Sure, maybe.
Yeah, see, that's what kept confusing me over the weekend when I was doing some of the homework for the chain rule. It was like I had the answer for a problem, and it was like I got it wrong a few times just because of I was trying to simplify it, and it was like already where it needed to be, and I didn't really need to simplify it. I was overthinking it. And then when I, like I finally got the answer, I was scared to put it in because I was like, well, and so I asked somebody to help, and they were like, you have the answer. Like, oh, okay. But yeah, it was
overthinking. It's a thing. You're not wrong about that. It's a little dangerous. Yeah, so that's what I'm saying. I wouldn't simplify it if you don't have to. Well, there's a couple of easy things you could do. You should be improving in your algebra skills. For instance, here's an x and there's some x's. And then this is a minus sign. There's a minus sign and a plus sign. So I might realize one of the x's cancel. So I'm left with 2 over x here. So 2 over x times the cosine of x. Since that's positive, I like that in front. And then minus the sine of x times the natural log of x squared. I mean, that's a nice looking answer. It's like, whatever. But that's all you can do. There's nothing else you can do with this. So, as a recipe for slope, I find myself thinking, wow, that's amazingly complicated. The original function was some crazy thing somebody made up. And now you're saying there's the recipe for slope. I found the recipe for slope. It's just weird that it would be that complex. I've got to speed up a little bit. I want to do a bunch of examples here, but let's see, how much time did I devote to this topic? Is it just 1 day or is it 2 days? 1. What about log? That was natural log. What about log of x? Is it also, you might say, well, is y prime equal to 1 over x again? Like, log and natural log are both kind of the same thing. But remember, log was base 10. Again, that was kind of like a hidden, it's base 10. It's assumed, but you just don't bother to write it down. So one thing you could say is, well, you could do what we did a second ago. Just a couple of options. You could do what we did a second ago and say 10 to the y equals x. What's the derivative of 10 to the y though? Is it 10 to the y? Remember, the derivative of e to the x is e to the x, but is e as e is a number, remember, is 2.718. Is that some special number? The answer is unfortunately it is. Let's try another option. We'll go back to that in just a second. You may remember one of the rules of logarithms is, like for instance, in your calculator, if you have the log of 5 base 2, you may remember this rule. Like you get all done solving something and you have log of 5 base 2, you can actually bust it because your calculator doesn't do base 2. It only does base 10. So if you say log of 5, you're not going to get the right answer to this. So you might bust out your calculator and you can say either natural log of 5 divided by natural log of 2, or you can say log of 5 divided by log of 2. It's called the change of base formula from Math 111. You can bust your calculator out and find that. So could we do that here? Could we say that's the same thing as the natural log of x divided by the natural log of 10? So again, what we're trying to do is say, can we change this to something else that we do understand? A minute ago, we changed natural logs to exponentials and we understood them. And now here we're changing logarithm to natural logarithm now that we understand it. So this one, we actually don't right now know how to take the derivative of 10 to the y. We will today, but it turns out because that base is not e or 2.718, the derivative of 10 to the y is not 10 to the y. We'll get there in a second, but we can do this. So this one has promise. Let's see, I could multiply both sides by the natural log of 10 just because I don't like fractions. I don't want to do the quotient rule. Natural log of 10 might bother you, but remember that's just a number. Like you could break your calculator out and that's just a number. That's like 5 times y, 15 times y, it's just a number. So now when I take the derivative of both sides, the derivative of, if that was a 5y, would just be 5y prime. So the constant just comes along for the ride. Natural log of 10 is a constant, derivative of y is y prime. And we know the derivative of natural log of x is 1 over x. So then I guess I just have to divide by the natural log of 10. So notice, and again, this I think is on the note sheet that I gave you. So I have it in front of me. I should look really quick. Yep. So notice the natural log, the log of x is still 1 over x. So it is like natural log, except for there's just one more part to it. Whatever that base is, if that base is a 10, then you also need a natural log of 10. Now, a minute ago, wasn't that an e? Wasn't that, I mean, natural log of x is log of x base e. Well, then sitting down here would just be the natural log of e, but that's unique because it happens to be 1. So that's why it kind of wasn't there for natural log. Natural log's derivative is just, what really was 1 over x natural log of e. It's just natural log of e is 1, so it's just 1 over x. So log's a little worse in a sense. It's got one more component. So in my note sheet then, I said if y is equal to the log of x, of course you want to say to any base. It doesn't just have to be 10 What if it's log of x base 3 or something? Then y prime would be, well, 1 over x. But then also natural log of whatever that base is. Like this is that's the fact of how logarithms work. Natural log is much more common and easier to work with. So that's kind of our second fact today. And it won't surprise me if there isn't even a log question in your assignment. I haven't looked at it yet, but if there is, it's not terrible as long as you have kind of your note sheet in front of you, know how to work it. What of, though, kind of our third for today, what about exponential? What about exponential equations? Man, my handwriting looks terrible. Let me show you an example of this. I have something kind of set up that'll go fast here. Where did I put it? Again, just to give you kind of an illustration for this. So notice this is curving downward. Again, this is a practical example because I just find that if I don't show practical examples, people don't connect with it enough. Anybody know anything about wood? Does it matter how dry wood is? Who cares? Your lumber's dry, so what? I paid my way through college in this world, the world of lumber. But I do a lot of woodworking now, and I bought a $1,500 piece of lumber that I built a table out of, and how dry it is extremely important because when stuff dries, it shrinks and twists and warps, and I needed it to be dry before I started work on it. If I got it all worked on and made it all perfect and then it warped and twisted afterwards, I would have been really pissed off. So like I asked them to test the dryness of it for me before I hauled it home, and it needs to be like 8%. Otherwise it's gonna continue to dry out and twist and warp and so forth. So, here's some data I found on the percent in lumber that was drying. And of course, you dry lumber just like you dry clothes. You stick it in a hot room. Try to keep it from starting on fire. But again, here's data. Here's real data that's curving downwards. Notice it's not a line. It's not a linear equation, but it's curving downwards. In the interest of time, I'm going to, just because I want to show you this really quick. Whoa, where'd you go? In the interest of time, I stuck this data already in a graphing calculator. I could just tell you the equation, but again, I just don't think people walk out of algebra knowing it as well as they should. So you don't remember the data because I just showed it to you for 2 seconds. But let's go in and do regression. So I typed all the data into the graphing calculator, and I'm going to go to stat and over to calculate. And because it's not straight, I'm not going to do linear regression. Quadratic doesn't make sense because although it went down, it's not going to turn around and come back up and get wetter over time. It's going to level out over time. And it just turns out that And man, this is a model for a lot of things. Exponential regression is a pretty good model of this. So write that equation down. There's what the graphing, and just round it off, like call A 46 and call B 0.84, close enough. I'm going to write it down as with you, so if you missed that. So from regression, we got y equals You guys tell me, what was it? 86? I forgot. I can't see it now.
46.
46. 46 times A, which was 0.84. Is that right? Is that it?
I think so.
Yeah, that's it.
Thank you. So exponentials equations come up in the real world. And again, notice this data fits the graph pretty well, actually better than the baby graph did just a minute ago. And so this is incredibly practical. Notice on the graph, I have kind of a dotted line there at 6%. And so you should be able to use algebra. I keep talking about algebra. You should be able to use algebra to say, if I wanted this to be at 6%, then since X is hours, you should be able to say how many hours this needs to stay in the dryer. That's an algebra question. Again, can you do that? Like that's why you're supposed to, that's why you take math. You should be able to say, great, leave it in the dryer and for whatever. Well, notice the graph tells me it's a little under 12 hours. The graph is good enough. I don't need to do algebra to answer this question. Looks like 11 and a half hours. Leave it in there 11 and a half hours and it'll be down to 6% moisture, and then you can take it out and sell it and everything will be great. Happy customer. So you should still be able to solve an algebraic equation like that, and it takes logarithms to do that. But again, what are we doing? We're saying, let's find the derivative of this. In calculus, we're saying that's worth something. But I guess what I want you to understand is you don't know how to do this right now. You know the derivative of e to the x is e to the x. But remember, e is 2.718. That only works in the situation where the base is e, 2.718. What's the derivative when it's something else? Well, like a 10 we saw a minute ago, or something worse. So let's tackle that now. So find y prime if y is equal to, well, some other base. That's our job. And we're going to get back to the blue problem in a minute where we're actually going to do a real question, but it's like, it isn't always E. So what are we going to do with this? Well, here's something cool. Remember, this is just an algebra equation, and you can do anything you want to both sides of an algebra equation. And all we're trying to do, and the logic of everything I showed you today, is just, can we change this to something we do understand? We might wonder, is the derivative of a to the x, a to the x? Maybe it works for every number, not just e. But let's do something that we algebraically can do. Like we've never tackled a problem where there was an x up there before. That's the issue. And unfortunately, it's definitely not the power rule, like the x comes down front and you subtract 1. That's definitely not true. It's not the power rule. It's worse than that. And again, you could just graph it and check. So let's take the natural log of both sides. You should understand why I'm doing that. If I took the natural log of both sides, then the left side would be the natural log of y and the right side would be the natural log of a to the x. But why did I do that? That just makes it worse, right? It looks worse. But why are natural logs cool? Why do you get them involved when you're solving exponential equations. What beautiful property do they have that's going to help us here?
They put everything in the denominator.
You're going the right direction with that. What's true about this x right here now?
You can move it to the front.
It moves to the front. That's why logarithms were invented. Like you have to have logarithms to solve exponential equations. The one that I listed back here where I put in y is 6. If you're going to solve that for x, you're going to have to get logarithms involved. The easiest way to get them involved is to take the natural log of both sides. And so now that x can fly down front, and basically now it's like, oh, great. Now there's no x up there. Now you should be able to take the derivative of that with what I taught you today. Again, I'm going to give you a second to see if you can figure this out yourself rather than me just tell you. You take the derivative of both sides. And let me point out that a is a constant. A is, we're not treating a like it's a letter. A is like 3 or 6 or 18 or.
So it's not a function of x.
No. Think of it as like 5. A is 5. Because that's what we have in our original problem. A is 0.84. It's a number. An exponential equation has a number for its base, but we're just going to try to figure this out for all problems instead of just for when a is actually 5.
Isn't the derivative 1?
That sounds too simple.
Because isn't natural log A just going to be a constant?
Yes, it is. And so what's the derivative of natural log of a?
Wouldn't it be 0?
Yes,
0, derivative is 0, yeah.
that's right. So when you get to taking the derivative of natural log of a, it's just natural log of 5. It's just a constant. It's a weird looking constant, but it's just 0. But notice that right side, though, is product rule. Well, let's do this.
Wouldn't the left side just be y prime?
Not just y prime. What's the derivative of natural log of junk?
1 over the junk.
1 over the junk. What does chain rule say we still have to do?
Multiply by y prime.
Multiply by the derivative of the junk. So that's the derivative of the left side. What's the derivative of the right side?
0.
It would be 0, but think product rule. Product rule is the derivative of x, which is 1, times the natural log of a left alone, plus the x left alone times the derivative of the natural log of a, which is 0. So again, that right side is natural log of a is just a constant. So in a sense, that right side is like saying, what's the derivative of 6x? Isn't it 6? The derivative of 6x is 6. That's what's left over here is just that constant that's in front.
So would the derivative be L in, or the natural log of a over y?
Do your algebra a little more slowly. Like I got to solve for y prime. How am I going to get rid of that 1 over y?
You multiply by y.
Multiply by y. So y prime then would be equal to y times the natural log of a. But what was y equal to? Because I really don't want it y's on both sides. So I could say, or another way to say it, since y was a to the x, it's a to the x times the natural log of a. So our third fact for today that's also in your note sheet, if y is equal to a to the x, then y prime is equal to a to the x. Hey, that's what e was. The derivative of a to the x is a to the x, except for there's times natural log of a tacked on to the end of it. Notice that's why e is so cool, because if it was e to the x, then it would be e to the x times the natural log of e. But the natural log of e is 1, and so that natural log part goes away if the number happens to be e. That's kind of cool.
Can you explain why the natural log of a, the derivative of that is 0?
Because we're thinking, we decided a is a constant. Like, in other words, for an exponential equation like the one we got in using exponential regression, we got a base that was just a number. Like, that's what exponential equations are, is equations where the base is a number and then the variable x is up in the exponent. That's what makes it exponential. And so that number, that base right there, we call it a, but we're trying to do this for any constant because there's all kinds of different bases for exponential equations, but they're always numbers. And so we did this trying to find the answer for any value, but a is a number. Therefore, the natural log of a number is just a number. If I take the natural log of 5, it's still just a number. So it looks weird. So yeah, that's a good question. It's good to bring that. Like a second ago, didn't we just say the derivative of natural log of junk was 1 over the junk?
I'm still confused.
Yeah, let me write this. I get
I thought
it.
it would be like 1, if it was like the number 5, I thought it would be like 1 over 5. I think I'm kind of with April.
So I agree with you. So isn't the derivative of natural log of junk 1 over the junk, right?
Right.
But what's chain rule say? You're not done.
Find a derivative of the junk.
Oh, you multiply it by 0 because it's
Times the derivative of the junk.
Oh, okay, that makes sense.
And so, yes, you can use that if you want to. But do you understand that? I mean, if I bust my calculator out and I say, what is the natural log of 5? Natural log of 5 is like 1.6. So I'm really just saying, y is 1.6. What's the derivative? Even though it looks weird, right? Because it's natural log of a number. It's really natural log of it's really y is 1.6. What's the derivative of that? 0. So that's what I'm saying. I mean, it's important to think, like, if you want to say the derivative of natural log of 5 is 1 over 5, knock yourself out. Just don't screw up the chain rule.
Perfect. Thanks for asking that, April. I was confused too.
Good job. Maybe I'll just leave that there. Yeah, that's confusing, isn't it? Totally get that. So just to kind of, I don't know, make this sink in a little bit, let's go back to this question then and say, all right, awesome. You found this cool equation that models the moisture content of lumber. And so you decide to see what calculus can tell you about it. You decide, I want to know, maybe I'll just pull that down below. Copy. Paste. So regression gave us this equation. And you say, I would like to know what y prime, and let's be specific, y prime of 6. In other words, I want to know what's the rate of change? What percent rate is this changing at hour 6? So you say, okay, cool, I got to take the derivative of that. So the 46 just comes along for the ride. We said, what did we just say? The derivative of a to the x is a to the x. So it's 0.84 to the x. It's a to the x. but then it's also times the natural log of 0.84. Do you agree with that?
Yep.
Now, I don't think I'm going to do this just in the interest of time, but this is a number and all of this is a number. Like I probably would, since these are decimals anyway, I'd probably bust out, actually, I think I will. If I take 46 times the natural log of 0.84, I get negative 8.02. So I mean, it'd probably be easier to write if I said y prime equals negative 8.02 times 0.84 to the x. And so now I can find y prime of 6. Negative 8.02 times 0.84 raised to the 6th power. My calculator says that's negative 2.8. Negative 2.8. I'll go back to that in a second, but does that make sense in this picture? What is that telling us about hour 6? Our last hour we collected data. What is that telling us about this?
It's decreasing at that rate at 2.8.
That's exactly right. Notice the graph is going down. So in a sense, maybe you didn't think about it before, but of course it came out negative. Aren't we dropping temperature? So it's actually predicting that if I took 16.2 and minused or subtracted 2.8 from it, that I'd be down to 13.4 at hour 7, or at least that's the rate of change right now. I'm dropping 2.8, roughly 3% an hour. Notice 3% per hour. But can you appreciate that it'd be higher here? Isn't that a steeper pitch, a steeper angle up here? It's more shallow down there. So I'd get a bigger number if I threw 1 in there. A bigger negative number, it'd still be negative. Again, these are reasons to do calculus. Like, why would you really be doing it? Your book is not going to show you examples like this to help you understand, like, why am I even doing this? Your brain is hurting, yes? I've jammed a lot of stuff into it today. Let's not do anything else other than let's just try a couple of examples. I'm just going to pick some. I'm looking at the book right now in your 3.9 section. I won't do any of the odd questions because I'd like you to have those for the back of the book, but let's just do a couple examples. Let's see. Oh, that looks, let's try this one. Whether this is hard to you is dependent on how much you had to learn today. If you stare at this and say, oh, minus sign, good. That means there's like 2 separate derivative problems here and I can ignore them. Awesome. If you look right there and see multiplication and think, oh, product rule. And then you should already know that in a sense. But again, I like these problems are here because it's not that we can't all improve. We need practice with this stuff. And the only thing that's really new today is natural log. I have natural log of something there. Okay, I know how to do that now. So product rule says derivative of x, which is 1 times natural log of x left alone. There's the first part of the product rule. And then there's a plus sign. And then the x gets left alone times the derivative of natural log of x. Derivative of natural log of x is 1 over x times the derivative of x, which is 1. So there's the product rule. That's done. Then there's a minus sign, and then, oh, much better. I like that much better. Derivative of x, that's just 1. I'm done. That's the answer. Does it clean up a little bit? In this particular case, cleans up a lot. Let's see, 1 times the natural log of x is just natural log of x, and so no reason to have the 1. And then this is x, second one is x divided by x, which is actually just 1. And then, oh, look at that, those go away. So apparently the derivative of x natural log of x minus x is just the natural log of x. That seems really weird that it got so simple. Seems like some math nerd must have made that problem up to come out really nice, simplify. That's kind of cool. Let's try another one. Just kind of want to give you some examples so that you can improve in your thinking, but I also don't want to go too fast. So if you have something you want to say about any of these, please slow me down. I don't know. What about this? What about the natural log of the square root of 3x plus 7? Is that terrifying? Notice that's not multiplication. That doesn't say natural log times square root. That's just the natural log of it. So there's no multiplications here. Good. I don't have to do the product rule. So this isn't hard. Derivative of natural log of junk, 1 over the junk. But we're not done because that's chain rule. That is junk. That's not natural log of x. It's natural log of junk. It's 1 over the junk times the derivative of the junk. And this time I am going to just write that down. In other words, I need to take the derivative of the square root of 3x plus 7. Well, it's like kind of its own problem. Let's see, what is the derivative of, for practice from before, the derivative of the square root of 3x plus 7? Well, that's the same, as you know, of 3x plus 7 to the 1/2 power. So its derivative, oh, that's just power rule. The 1/2 comes down front. The junk inside stays unchanged, but I subtract 1 from the exponent. But even that is a chain rule problem, because even there I have to say times the derivative of the junk inside, which is 3. Whew. That's messy. So apparently y prime then, so basically all of this is replacing that derivative. I just felt like I was going to get confused, so I just wrote down that I was going to do it. It's too many things, too many steps. So actually this is the chain rule inside of a chain rule. It's like natural log of the square root, but then even that, it's not just the square root of x, it's the square root of 3x plus 7. So it's like a 2-step chain rule. So let's see, what do I have? Well, I've got the 1 over the square root of 3x plus 7. And then I've got to multiply by this mess. But isn't that 3 on the top? And that 2 is on the bottom. 3 times 1/2 is 3/2. And then since that 3x plus 7 is to the negative 1/2 power, couldn't I move it to the bottom and have it be positive 1/2 power? I don't like negative exponents. I'm just saying that practically, like I got to plug this in. And what's incredibly wonderful about that? Well, you can actually multiply these two together. You don't have to find a common denominator to multiply fractions. So you end up with a 3 on the top, a 2 on the bottom, and then when you multiply the square root times the square root, doesn't it go, the square root go away? So apparently that's 3 over, there's no reason to leave that not multiplied, I guess. So I'll say 6x plus 14. That's almost hard to believe. So you're saying the original problem was natural log of the square root of 3x plus 7, and its derivative formula is like 3 over 6x plus 14. That just almost, it just seems like that can't even possibly be true. And I'm not kidding when I say that. That's kind of what I'm literally thinking that right now. Like, you got to be kidding me. Is that really true? Again, to give you time to soak on this, I'm gonna go to Desmos and graph this, because I almost just can't even believe this is true. This can't possibly be true. Let's see, I think I can reuse some of this. So the square root of 3x plus 7. Yep, that works. And
Mary Montague.
oh, all the times to call, I need to talk to you. Ugh. It's not good. And I'm even going to do something cooler, and I'm going to make a point called a f of a. And now I have a slider for a, so I can slide along my crazy natural log curve. So notice this is the graph. That's the graph of my weird f of x graph. So I can slide along, and notice now down here I can see what the derivative is. So isn't that kind of cool? Like, I can slide along and like get a free derivative every place I go. Notice the derivative is getting smaller and smaller and smaller because it's getting flatter, right? Whereas like back over here, it's kind of steep, and then it gets really steep. And so there I am. Let's see, let's go to -2, just because it's a nice whole number. I go to -2 and the slope is 1.5. So what I'm wondering, that I just can't even believe is true, is, I took a picture of that screen. I got to get it back up. We're saying that this other equation, g we're saying g of x is actually the derivative equation, and incredibly, it's 3 divided by 6x plus 14. It just doesn't seem possible that that would be the derivative. I'll turn the graph off just so that you don't have to look at it. But now I'm down here, and I'm going to say, okay, great. If that's true, then tell me what g of a is. Look at that. Seems to be working. F prime of a is 1.5, and g of a is giving me the same slope. And so if I slide somewhere else, yep, g of a, g apparently is the slope equation. That just seems crazy. Like, the square root's gone and the natural log is gone. Like, just doesn't that seem weird? Yet apparently it's true. Unbelievable. What a world we live in. I feel like what we need is 15 more minutes to just do more examples and try to give you a chance to soak all this in. But this is an important chapter because it just represents a lot of practice. Like, you have to know the natural log of derivative natural log of junk is 1 over the junk. But there's still going to be product rule and still going to be chain rule. All that stuff is still going to be mixed in. And, we need practice in that stuff, I guess is what I'm saying. And let me just warn you one thing with respect to the assignment, because I'll spend a few minutes tomorrow talking about this, because there's one thing we didn't get to, and I'm kind of glad, because I feel like we covered too much stuff today. We use the same logic for everything. I would encourage you to go back over my notes and kind of, recreate this stuff. Let me show you just one other thing. I'm just pulling up the note sheet that you have in front of you. I would encourage you to, since I did this for you, again, I didn't prove formulas to you, I built them for you. There's a big difference there, I think. So we made all three of these today, did we not? What I'd encourage you to do is try to go do those yourself. Try to make those for yourself, like from scratch. Somewhat based on memory, but also somewhat based on logic. You know, and then look at my notes if you need to. I just think the confidence that, hey, I can make these for myself is kind of cool. I don't need somebody just to tell them to me. Secondly, I need to show you one other thing tomorrow. And if you get into the assignment, which you should, I'd love to start tomorrow with, you know, hey, I couldn't get question 7 right. You have clear till Sunday, so we have a lot of time. You should be able to wade into all but the last couple of questions. And here's what you can't do. I'll shut up after this. You couldn't do something like this right now. If I said, what's the derivative of the tangent of x raised to the x power? Why can't you do that? Because this is not constant. What you learned today is how to handle it if that is a constant, but what if that's even an equation? You can't do that yet. Well, you could if you use the technique that I showed you to solve this in the first place, which is take the natural log of both sides. Remember, if you take the natural log of both sides, that x can come down front. Like that's what I'll show you tomorrow. Again, this is just mathematicians being knuckleheads. Like what, you know, whoever needs an equation that looks like this, does that ever model anything? What does that graph even look like? You can't do that yet without a little bit of thought. So when we get together tomorrow, the first thing I'll do, if I remember, is take the natural log of both sides of that so that the x can come down front. And then I will have the natural log of y on this side, and I'll have x times the natural log of the tangent of x on this side. And now it's like, oh yeah, x times junk. Hey, that's product rule. Like you can do that right now, if you understand what I just said right there. But let's tackle that tomorrow. There's too many things for today. All right, shutting up. Stay after if you want to talk. Otherwise, I'll see you tomorrow.
Hey, Doug, I kind of having a mental block on my project. I was wondering if you could take a look and give me some hints on how to proceed.
Happily.
You mind if I share my screen?
I do not. Let me give you that power. You are now a co-host.
All right, so just kind of from like watching you in the previous class, I thought I had to define A of H right here, but it's not loving it. It's saying I need to define H in more than one place.
Slide that over so I can see the rest of your equation.
Oh. So this was the derivative.
Yeah, got it. So your problem is just that you actually want a number for H, and you have chosen A to be 1, and A is X. So that means all those X's you have up there, those need to be in the H equation, not that one, in the next one, that one.
Oh.
In that equation right there, those should be A's now, because you're actually saying, I want to use this to find a slope at a particular point. So make those all A's.
I think I tried that, and for some reason it didn't work super great for me. And do I keep this as Y or do I put it as H?
Let's see. Yeah, that's a problem, because you're going to have H in more than one spot then. So go change that first, that negative 0.6x, change that to an A.
Negative 0.6x. Oh yeah, sorry.
An A. And then
Oh, right.
now let's look at your top equation.
Okay.
that top equation can be solved for y. See, the problem is in the equation you were just working with, if you go down there and put an h in it, it's going to say, well, go ahead and try it. Let's see what it says.
Okay.
I think it's going to say you can't.
Oh,
Does that work? No, it doesn't work because notice it's not on your graph. No, let's see. H. Drag A around a little bit, see if it stays on your graph.
oh, drag A around.
Try it. Yeah, next line down.
Okay.
Dragging it over there. Yeah, see, I think it doesn't like the fact that you're saying H equals, and then on the other side there's an H. You see what I'm saying?
Yeah.
So look at your top equation now. Could you
Yeah.
solve that for y? What would you do to
Uh,
solve that equation for y?
So I would do 10 times sine to the y, and then, and I have it written down. I would just basically try to get y prime. I was trying to get y prime by itself, so I ended up dividing by sine y. I think I ended up with sine y times y prime, or like cosine y. Excuse me.
Yeah, so you don't need. Let's assume you're. Let's see. Wait a second. What is H? Is H a slope or is H the?
Well, yeah. So I just took a of h from, like, I kind of saw you doing it. I saw like some other people doing it, just defining it right here. But I didn't know what h was supposed to be. Is h supposed to be the slope? But
Well, there's two things you need to calculate. One of them is the y coordinate. In other words, when you say, like right now, you're saying x is 2.1, right? You're saying the point I'm at right now has an x value of 2.1.
yeah.
So h is the y coordinate for that. And that's not the ugly mess you have there. What you have typed there is I think a slope.
Yeah, it's a slope.
So get rid of that h, like right where your cursor is, backspace and say m, because like that's a slope. You're saying,
Okay.
I think I took the derivative, right?
Yeah.
So now make a new line that says h. Now see, you can't, right now you have h down at the bottom as a constant you chose. And notice if you do that, then it isn't on the graph because you're picking a and h, you're picking your x and y coordinates, your a and h, to be anything you want them to be.
Gotcha.
So get rid of that bottom one. I don't know what you just got rid of, but I'm a little.
I got rid of a because I don't want a to just. I don't want to pick a either. I want a to be a part of my graph, right?
No, you do want a, like you.
Oh, here you go.
So yeah, let a be there. Now what you got to do though, so let's go to that top equation. And now up there, x has been chosen, and don't think of it as a, think of it as, well, 0.1, like x is 0.1. Would you agree you have a decimal on the left because 0.1 cubed times 0.3 times cosine of 0.1 squared is just a number.
Mm-hmm.
And that equals 10 times the sine of y. Well, how are you going to solve that for y? Like you have to solve that for y so that you know the y coordinate that goes with x is 0.1.
Okay. I think I was trying to make the slider the extra credit like from early on. I thought it would be easier if I just kind of did everything from the start that way.
That's mentally difficult.
It is. Okay. All right. I'll play with it a little bit more. I think that helped me a lot right there.
Yeah, you still have time for more questions, but the main thing is you got to solve that top equation for y because y depends on x, and that h that you need is the y coordinate that goes with the a that you chose so that the point slides along on the graph.
So are you saying this y or h can't be down here?
No, it can, because in a second that your next move is to figure out what h is.
Okay.
And you should be able to do that. If you take that top equation and you pretend a is 0.1, you should be able to solve that for y.
Okay, cool.
Try it, and then we can talk some more.
All right, I will. I'll let someone else ask if they want to.
You can stay on and try it now. Maybe you ask me a question before you even leave.
Okay. So,
Adrian or Justin, either of you have questions or are you just hanging out?
No, I was just kind of watching.
Yeah. Capture a few things. Not a bad move.
Yeah, I was just trying to kind of watching too.
Yeah, that's not an easy thing to get your mind around because his top equation has X's and Y's, and there are billions of answers to that, which is why you get that crazy purple graph that he has. So when you have X and Y in, X and Y are not specific numbers, they're every number. That's the key. Where
So
when you jump down a line and you say, okay, now I'd like one particular point because I want to know the slope at one point. And so you call it AH, but those are going to be, that's going to be a particular number. Now you want A to slide around. You want A to be able to be any, you want it to be a number, but you want it to be one particular number. And so on his screen right now, A is one. Great, A is one. But, you know, what's the one point? I mean, on his purple graph, he has a million points. What's the one point on that graph that he's at right now? Well, if he's at A is one, you should be able to figure out the Y value that goes with it. And now you have a one specific answer, which is what gives you a dot, if you will, on your graph.
So do I replace A right here with the answer I got? So A is, oh, sorry. A is one that we discovered. So if the answer I got for H is 0.999695, basically. It's big decimal.
So try that.
So plug it in for H.
Yeah.
0.695.
Notice that appears not to be true because it isn't on your graph.
Shoot. All right.
And ultimately, we needs to go there.
Is
Yeah.
Is like F of A, right?
Yeah, it's kind of like,
Oops.
it's the formula, because what you just did a second ago, and by the way, maybe you moved A. Was A 0.1?
I put A as one, so I just did 1 to the third, which is 1.
Yep.
Times, and then cosine of 1 squared.
And that's also times 0.3. Did you forget the 0.3?
Yes, I did. All right, this 1 times cosine. Okay, so I'm gonna try this.
And so the problem with these, yeah, try it. Let's see if it works. Zoom in on it a little bit. Yeah.
Here, let me try going out a little bit further. 0. 6. Well, that's not working.
Turn that red graph off just so it's not in your way. So tell me what you did. Once you got that number on the left-hand side, what did you do?
Once I got the number on, once I got A, you mean?
No, I mean on the left side of your top equation. Once you stuck 1 in, you got number.
Oh, I just got the answer. I just put 1 in. Sorry, I just completely spaced on the other side.
Got it. So that's just, you're a long ways from solving for Y. You still got to get rid of the 10 and the sign.
Yeah, so I gotta divide by 10 then, right?
Yep. Then what?
By 10, and then
See, that's what's different about these equations, because your right side, we're used to looking at equations that are solved for Y already. Yeah. But in these graphs, you get really cool graphs, but it kind of comes at a price because the equation is not solved for X or for Y.
Yeah. So do I have to get?
You have to do it.
So how do I get Y away from sine?
Yeah. What's the opposite of sine? If you have sine of something equals 0.2. Look at your calculator screen. What's the?
Oh, there it is. All right.
What is it? Say it out loud.
It's I forget what sine -1. I forget what it's called.
That's right. Inverse sine or arc sine.
Inverse sine.
That's right. And because yours involves trig, you got to make sure that your calculator and Desmos are both in the same mode. Like make sure both are in radian mode.
Okay.
Maybe you already did, but that's important.
All right. So I ended up getting sine revert. What's it called again? I'm sorry.
Inverse sine. Inverse
sine of what was it? 0.2999. So I ended up coming out with a very similar answer, unfortunately, I think. 5, 3, 6, 1.
Did you divide by 10?
Yeah. So I did the answer of this, which was that big decimal, divided by 10, and then inverse sign.
So it was like inverse sign of 0.03 then?
Yeah, basically.
Look at your calculator more closely because it's not what you just typed there. The inverse sign of 0.03 is not 0.2999.
Well, I did the specific. It was 0.299, but we'll just do 0.03. There we go. 0.
Just 0 in front of it. That was my point.
Yeah. Okay. 4, 5. That's far enough out.
Notice it's,
Not quite there.
but that's just because. So the question is, can you redo that except for where X is A? Like you don't have to do it for 1. Redo it as though it's a formula.
So are we still, so is this H? Are we still calling that H?
Yeah.
Sorry, we are.
Yeah.
Okay. So if I wanted to do a formula, can I move this up here? Can I do H equals
You can copy in this too.
oh, you can?
You
Okay.
grab that chunk on the upper part up there and just,
Do that. Whoop,
yeah.
sweet. And then parenthesis that. Whoops.
Doing great.
Over 10. So it'll be 10. Oh, and then that needs to be
Beautiful.
then can I just do, I wonder. Does that work? Oh,
Sure.
sorry, I have to find the logs now. Where are those bad ones in? Functions.
I'm not sure if that works. Yeah.
Oh,
I
I
know
figured
that
it.
works.
Okay. So
So now turn the graph off for that because you don't want that to graph.
no, but then do I put H right
Yeah,
here?
exactly, because you just found them all. Do you see the difference?
Yeah.
And then secondly, does it make sense that you need to replace the X again with A in the equation you just made?
Yeah, okay, that makes sense. And okay, now we're on the graph.
Yeah, baby.
Uh-oh. So it gets undefined, which is fine, right?
Yeah. The problem you'll have, like if you zoom out on your graph, like right now you're at A is 4.6. Do you notice there's like hundreds of places it could go?
Oh yeah.
Don't worry about that. There's not a way to get it to slide like to every single place you want it to slide. As long as your point is on the graph and there is a tangent line on that point,
Yeah.
then you're good to go.
It's cool that it jumps from bubble to bubble. I like that.
Yeah. It basically doesn't exist. Notice how your graph doesn't exist at like 6 and 7.
Yeah, like all the
It
places in
goes
between the
nowhere.
bubbles.
I mean, that's a really cool graph. Isn't that weird that one equation could describe something so cool? It's just,
Yeah, I kind of fell in love with it. I knew that it was like a little over my head, but I was like, I want to make it work. I even gave it a little name up here, Bubbles of Wall. Had to happen.
I love it.
All right, so now I just got to make that tangent line, which I think I can take care of myself.
Yeah, and you might have some mistakes in your slope. Who knows? Like you might have blown the derivative of that. That's not an easy equation, but I'll help you with that. If you know it doesn't work, then let's talk after class tomorrow and say, what did I do wrong here?
That sounds awesome. Thanks so much, Doug. I appreciate it.
Good job. Yeah, anytime.
Take care.
Yeah, see you tomorrow.